Yeah, let's get it. I think we all got it. Okay, here we have a diagram of how the light travels inside the fiber. All right. You see that the light enters the fiber, and then it passes through the core at an angle. And at some point, it's going to meet the cladding. And at that point, Snell's law and the angle of dangle is equal to, never mind, you know the rest of it. Yeah. Okay. Pushes it back into the core. Okay. So you see that we have the angle of incidence is equal to the angle of reflection. Okay. And there's several different kinds of multi-mode fibers. One is called the step index, in which there's a solid boundary between the core and the cladding. That's great. It leaves for a simplified system. It's somewhat cheaper to build, but as usual, yeah, it's cheaper to build. So the downside is that there's a lot of pulse distortion in that. And as a result, the data rate that you can get is pretty low. So to fix that problem, we went to something called a graded index fiber, which means that the index of refraction changes from this middle of the core, and then it gradually changes over the cladding. And as you can see, instead of bouncing the light back in, it kind of nudges it back in nice and simply at a nice angle. We got a much better looking pulse coming out of it. Graded index fiber is pretty much what most people use in data centers today, and it's capable of hundreds of gigabits of performance. The carriers, they don't want to go 1 or 2 kilometers. They want to go a really long distance. All right. So we have what we call single mode fiber that has an extremely thin core and a very well-defined cladding there. It only supports one path through that fiber. That's why it's called single mode. Each path through the fiber is called a mode. Multi-mode fibers have many paths. And the last time I actually did a serious calculation of one of those things, a short length of 62.5 micron fiber had 17,000 something discrete paths through the fiber. And that would be terrific if we could figure out how to uncouple one path from another and get MIMO in the fiber. But nobody has figured out a practical way to do that. In the single mode fiber, the design spec calls for most standards for 40 kilometers at rates of hundreds of gigabits per second. So that's a really long distance, and it's a really good thing to see. Okay. The cladding is necessary to keep the light in the fiber. And if it wasn't used, the atmosphere would be the cladding material. And of course, it's not going to trap the light in there in a controlled way. For our total internal reflection, a portion of the energy in the electric field has to penetrate the cladding, and it's called the evanescence field. Typically, the penetration depth is 5 times the respective wavelength. And the cladding material's extremely high optical performance because there's a lot of the energy is being transmitted. It's bouncing that energy back. Right? You can find it in the core. So both the cladding and the core are necessary elements of fiber. Okay, next slide, please. Do we have a disconnect between? Oh, okay, here we go. So for fiber performance measurements, how do you know if a fiber is good? We have something that we call dispersion. And dispersion is the lengthening in time of a pulse. From when you transmit it, you have a steep waveform going in, but that steep waveform is distorted by its trip through the fiber. This stuff also happens on coax too, guys. I'm not just talking about fiber. Okay, so there is pulse distortion on coaxial cables, and it's an entirely different field. I just want to mention that there is an analogy here. All right, so we have modal dispersion, which is paths. Okay, there's different paths going through the fiber. So on multi-mode fiber, our pulse distortion is measured in what we call megahertz kilometers. How many megahertz can you get per kilometer going through this thing at a specific transmission wavelength? So Modal dispersion is a function of the longest and shortest guided light path through a fiber. A good quality fiber will have 2,000 megahertz kilometers for multimode fiber, meaning that if you go for 2 kilometers, you can get 1,000 megahertz out of it. If you go for half a kilometer, you can get 4,000 megahertz out of it. So you can estimate readily what the data rate you can get through the fiber is by knowing these numbers. And the manufacturer tells you those numbers. All right. Another kind of dispersion is called chromatic dispersion, and that's a function of what color the light is. And the color of the light is basically what frequency is that light going through the fiber on. Most of the time when you're using a fiber, you cannot see the light going through it because optical fiber transmitters operate in the infrared range. And if you look at the drawing on the bottom right, you'll see that we have what we call windows on a fiber. The optical fiber opens up, and the window is the area that has the least amount of attenuation for a specific purpose. So we have LEDs. Oh, very good. Yeah. Okay. I was talking about the windows that we have on these fibers. Okay. And the window is the area where it has the least amount of attenuation. Okay. And fiber optic has bands. A lot of us that work with microwaves knows that we have L-band microwave, C-band, S-band, K-band. Optical fibers have the same thing. They have this notion of bands that correspond to different wavelengths of light. And here you see them on a chart over here of second and third windows being the O-band and the S-band. O-band and C-band. And we have some other optical fiber frequencies in use there. Here we see that there's a water peak in which our attenuation in dB kilometers is pretty high. This particular fiber that they took the sample of is probably not a really great piece of fiber. The best attenuation that it looks like we're getting is about 0.4 of a dB per kilometer. Imagine getting that on a coax, 0.4 of a dB for a kilometer's worth of coax. Most of us would be thrilled to death to see that. Of course, it doesn't happen. Here we have a bandwidth comparison. There's different grades of multimode fiber, and they call them OM3, OM4, and OM5, which is wideband multimode fiber. And here you see the wavelengths of light that it accepts. On the top right, we see that there is a visible spectrum. And unfortunately, I got this from the internet, and it's backwards. It doesn't correspond to the graph on the right. Just flip it. You can get it. But this is the visible light that you can see. Typically around 700 nanometers or so, we have the near infrared, and then it goes all the way to ultraviolet, which is around 400 nanometers. The visible spectrum does not work very well on optical fibers. So we need to use different kinds of transmitters for it that work on the areas that the fiber has a little bit of attenuation. Okay. So most of the operating specs on the fiber you'll see that we're going to be using are the third window, which is considered the C-band. That's around 1550 nanometers. And the 1300 nanometers, 1310 nanometers, that's very common for the second window operation. And local fiber, going a few kilometers at relatively low data rates, are going to be using the first window, and we use that because it's the least expensive. Okay, next slide, please. What's wrong with it? Change the slides. I don't know. Okay, good, cool. Okay, if we really want to use that fiber, we could do something called wavelength division multiplexing, which on a coax, you'd probably call it frequency division multiplexing. And on a fiber, that means we can use different colors to operate independently of each other. And all we need to do is put a prism there. So of course we can get a precision prism, and we can do a few wavelengths of fiber, combining them. And we get what we call coarse wavelength division multiplexing. It uses a few well-separated wavelengths. It uses relatively inexpensive equipment. And that is how FiOS works. For any of us that have FiOS with fiber to the house, it uses coarse wavelength division muxing, and it puts telephone, the old analog television, actually becomes digitized, and it has its own wavelength on the FiOS fiber. Then your internet has its own wavelength on the FiOS fiber. And then the television band comes in with a whole different wavelength on the fiber. So the FiOS is actually multiplexing several wavelengths at once. For precision long haul, and I'm thinking here of submarine cables that go literally tens of thousands of kilometers, you really want to make the best use you can of that fiber because those cable laying ships are expensive as hell. So what they do is they use dense wavelength division multiplexing, and it can use up to 256 wavelengths, and it requires extremely high precision optics. The colors on these things, the wavelengths of each transmitter have to be very carefully selected. They're very temperature sensitive, so we have the equivalent of crystal ovens for optical fiber transceivers on these type of systems. Okay, next slide. Okay, let's take a look. I mentioned that we have fiber optic transmitters and receivers. So here we do, we have LEDs and lasers. And we also have something called a vertical cavity service emitting laser, which is sort of a cross between an LED and a laser. Okay, for an LED, relatively cheap, emits a very broad cone of light, doesn't have a whole hell of a lot of power. On the other hand, LEDs are really cheap. And they go up to a gigabit these days pretty easily. Most of you that may have an optical fiber thing home, in your power side, typically you get a gigabit per second and you can go a couple of kilometers with that piece of fiber. Not bad. And there you see its profile. And it has a broad spectrum of light that comes out of it. It's just not that precise. A VCSL concentrates the light in a smaller size, and it has a narrower spectrum. Then we can go to a laser, which is the only practical way to excite a single mode fiber. The lasers are expensive and they consume a lot of power, but on the other hand, they're much faster and they have a much cleaner profile. So here you can see that the laser matches pretty well with the single mode fiber, simply because of its small spot size. Okay, next one. Okay, with a combination of techniques, we can get to really high speeds here. Given that we have a 10 gigabit transceiver, we can use parallel lanes as a standard. We can do 40 and 100 gigabits per second. 40 gigabits per second is done by having 4 strands for transmit, 4 strands for receive. And then they combine and uncombine by a technology that's called bonding. At 100 gigabits per second, we can use 10 strands of 10 gigabit things that will also bond together. And to go to 400 gigabits, it's just not practical because that means that you need to jam 80 fibers into a single connector with precision and no alignment problems. Tough to do. The connection people have tried, and it's getting it to a reasonable cost is tough. Okay, then we have 25 gigabits, which is somewhat newer. You can probably tell that we're going to run into a speed limit with the fiber because of a chipset that's called the SerDes, which is serial deserializer chip. These chips today are topping out somewhere around 25 gigabits per second. People are working on the semiconductor. People are working on getting them up to 100 gigabits per second, but I don't think they're quite there yet. Anyway, our standards for 40 gigabits using 25 gigabit parallel lanes, that's not available because 40 is not an even multiple of 25. But to go at 100, we only need 4 strands in each direction. All right, and then for 400 gigabits, we need 16 strands in each direction, and that's about the practical limit of our connector technology to keep all those things lined up. All right. Another technique that we can use is to use wavelength division multiplexing and parallel strands. And here, by using some coarse wavelength division multiplexing and a few multiple strands, we can get 400 gigabits per second with a reasonable number of fibers. And this is what we're doing in a lot of data centers today. Okay, coming out of a CO, it's a single mode fiber, and it goes through splitters. In other words, you don't have the whole fiber for yourself. They have it shared, and there's a spec called ITU 984, which is the spec on how to do it. It's called a passive optical network. And in the past few years, those things have become very popular. Yeah. Okay. Okay. To splice a fiber, they have a specialized equipment that does it. It actually melts the fiber, and it put them together, and you have an alignment tool that actually lines them up, and it does it. And you'll frequently see these things out on the street. Typically, it's done in the truck. They pull the fiber out of the manhole. It goes into the truck. When they get it spliced and working properly, they then put tape, some sort of a tape around the fiber to protect it. And it goes back into the manhole, and then they move it. Well, okay, the question was, after you splice a fiber, is it as good as the original, or is there some degradation? And the answer to that question is, if the splice is done properly, you can't tell it from the original.
One final question. At one time, with the undersea cables going across the Atlantic, I believe they had problems with sharks chewing on the cables.
Yes.
And has that been resolved, and how did they resolve it?
Okay. They found out that the sharks chewing on the undersea cable was a result of the power frequency that they used. In other words, to go underseas, you can go 40 kilometers, but then you need a repeater. So an undersea cable typically has quite a few repeaters along the way, and those are fed by relatively high voltage lines, a couple of kilovolts. Copper lines are embedded in there to power the repeating equipment along the way. What they found is that the AC on those power lines actually was attracting the sharks. So what they did was they experimented, and they found a method that excites them well enough without getting the sharks going into a feeding frenzy. So they were able to take care of that problem. However, some cables are subject to things like boat anchors hitting them, and when that happens, the cable is severed. Huge problem today on the internet is the country of Egypt. And if you look at the connectivity between Europe and Asia, the shortest path runs through Egypt. So last time I looked, there were 7 major cables and probably 50-something not so major cables all running through Egypt. And it's also a major shipping area, and there are constant problems in that area with boat anchors literally dragging along the cables and breaking it up. So there's constantly cable activity or repairs in the area around Egypt.
Just as a rough factor of comparison, if you had to replace any one of those replace one of the fiber cables with a microwave, how many times would you have to use one microwave connection to try and replace one cable going from Europe to Egypt?
Okay, a typical undersea cable may be 10,000 kilometers long. A typical microwave hop is probably 2 kilometers. So just do the math. And you need an impractical number of them, especially since they'd have to be floating in the middle of the ocean. Yeah, it's just not practical.
I was thinking more for the short haul, and I should have said that. If you had one big microwave link versus the fiber, how many big microwave links would it take to cover one fiber? Just
Also consider that the bandwidth of the fiber is likely to be way, way greater than the bandwidth of the microwave link. So you're talking not about one microwave link, but maybe 50 parallel ones. Yeah, assuming you could get all those frequencies for a microwave, good luck with that. And then to get an equivalent data rate is just ridiculous. I mean, it's not happening. Yeah.
George, those splices, they don't make them flat. They put them on an angle, right? So they don't get reflection of light back.
Right.
Okay.
Right. If you ran a flat splice, what happens is that would create a potential mismatch. You might get some reflections, the equivalent of SWR in a coaxial cable. And if you do it at an angle, the cutover is much smoother. And as a result, there's less transmission loss and so on. So, right, they are done at an angle. And in fact, on single mode fibers, the connectors are made to have a very specific angle, which I think is about 4 degrees, but I'm not really sure. 4 degrees from center, from 90.
So an 811 story, in case anybody doesn't know what 811 is, before you dig, you're supposed to call 811. Well, the town that I worked for thought that they were smarter and dug a hole and accidentally broke one of your fiber optics. How much would that cost an average for a fiber optic cable that's underground?
There's so many variables with the cost of fixing a fiber that is broken. One is that one has to assume that the fiber was designed to be fixed, which is something that the carriers do, but not necessarily anybody else. So there's a whole host of things coming up to a cost.
It cost them quite a fortune when they were finished, because I don't think they were able to just fix it. They kind of like pulled it when they dug it up.
That happens. Yeah, okay. Here's a very important part about fiber, which is keeping them clean. Because the fiber cores and the cladding are so small in diameter, you know, anywhere from 62.5 microns to 8.7 microns, it's difficult to keep them clean. Every time you open the fiber, you expose it to dust in the air. And let's say that dust is concrete dust, which is pretty common just about everywhere, but especially in manholes because they're made of cast concrete. And that material that the concrete is made of, concrete dust, is a little bit of silicon in it. It's very, very black. And here you see what some of that dust looks like. It blocks the path of light. All right. So we have to be careful and make sure these things are clean. If that material is on a laser excited fiber and it gets very dusty, the laser has so much power per square meter. Now keep in mind that the laser may have a couple of milliwatts in it, but in reality, we're not talking about a square meter. We're talking about a nanometer, a really tiny area. There is so much energy into that dust that the dust catches on fire. And it's actually been known to melt fibers and spread because of the fire. So fibers have to be kept pristinely clean in order to work. All right. So always keep dust caps on the connectors and anything else that's going to have a connection. Try and prevent the dust breakout, and always check your fibers for dust. Actually, they have fiber optic microscopes that you put the bare fiber into, and you can actually see the dust, and you can tell if your cleaning method is effective. Okay. One other very important point over here, it's on the top right. It says, caution, do not stare into a fiber with your remaining eye. Yeah, watch out for that one. Okay, next slide, please. Okay, now, how do you make a fiber? And it just so happens that I have here, what I have over here is a fiber optic preform. This is actually going to be a chunk of fiber that goes on the top of a drawing tower, which is about 50 feet. You see it I think you could tell which piece of it you can tell from what I'm holding here. This gets heated to a couple of thousand degrees, and it gets drawn out. It gets smaller and smaller as it's drawn until it becomes 50 microns or 62.5 microns or 8.7 microns. And it gets spooled after it's aged. And that becomes your fiber. So this is a piece of fiber that has not been spooled. It has not finished been made, but this is the preform. This is the glass that the fiber is made of. And if you look at this one, the only reason I got it is that we're going to throw it away because this piece was no good to begin with. I'm going to let you guys come up over here and take a look at this. See if you can find the one. Okay? I just don't want to pass it around because it's not there. And
Okay. My experience with fiber optic cables were in some of the scientific instruments that I worked on where we were using them for ultraviolet light from about 200 nanometers up to 1,000. What we ran into there were, I'm working in a laboratory. I have no fancy equipment for really testing a fiber optic cable properly. I found a bright fluorescent light, held it up, looked in the other end of it, and if I could see the light, I said, well, it sort of works.
here,
George, can you speak into the microphone?
yeah, wow. Sorry about that. Yeah. No, that's okay. That's okay. Basically, this is the last slide of my presentation, and we're almost done. But I'd like to have you guys come around and see some of these things for fiber actually working. So I have the flashlight test, which Bob just said is the fluorescent light test. And any questions from the guys online? Yes, can be used for RF. RF in the form of light. That's how Fios works. The power level of fiber is a few milliwatts of light on a laser, distributed across RF modulated lasers, and they're picked up by a photocell at the other end, and they become converted back to electricity and becomes your entire cable TV spectrum.
George, when I was working on the E2D with Northrop Grumman, if it isn't working, I can't help that. Okay. We were working on these $150 million airplanes with fiber optic cables between the pieces of equipment.
Yeah.
And we had no test sets. We were using flashlights.
I can think of at least one E2C thing that got fixed with an MFJ 259 analyzer. But yeah, that's another.
I know that with the cell towers nowadays, in the old days, they used to have fiber optics go to the cell site. They'd have transmitters on the ground and run big, long coax all the way up the tower to the antennas. But they found they had too much loss. So now they put the transmitters up on the tower and they actually send fiber optics up to, up to that point.
Sure, it's a much cleaner interface. The only problem is the maintainability of that tower requires a
Brief follow-up. How do you diagnose it with the MFJ 259? Briefly.
I was the supplier of the MFJ 259. However, my friend over here, who mentioned that he actually worked on those things, is the person that actually did the test. So, Yeah, you just don't want to go for either. What?
No, it wasn't for fiber. That was an RF link.
I thought it was on the U2.
Yeah, it was, but it was the IFF antenna impedance.
Oh, okay. So you think-
There was a problem in the transmission line. It wasn't. The MFJ did not go up to the same frequency as the antenna. But I was just checked to see I was getting a repeatable SWR. And when the defect popped up, the SWR would change. But it was for RF, not fiber.
No fiber.
Hi, George.
Yeah.
Hi,
You're
George.
saying
It's,
out in the
George.
air, not in the
Okay,
fiber.
we have a question from the floor, question from our virtual room. Go ahead.
Yeah, hi, George. It's George, KD2FIU. Just wondering on the long haul cables with the transatlantic telecommunication spans, how did they ever deal with the Bentic storms, ocean storms that were actually fluxing the cables to change frequencies and or being destroyed or have latent problems after the storms were done? Was there any accommodations for that?
Well, sure. The fiber cables, when you put them undersea, they have to be protected. So there's all kinds of layers of special material that they have to be embedded with. And remember, you're not just talking about the fiber for these cables. You also have to worry about the power supply for the repeaters along the way. And there's a great deal of thought and energy that goes into that work. And there aren't very many standards. Most of these things are custom made for the specific cables and transit paths involved. Also, the technology has changed quite a bit over time.
Oh, yes, I understand.
That's
I
not
understand the
best
technology.
That's probably not my specialty. My specialty is more like wiring a data center with a bunch of fibers. So,
Okay, yeah, okay, very good, because they probably had to come up with some way to deal with either flexibility issues or self-repairing issues with extra capacity in the cables, because tremendous storms would actually fracture the cables so that they were not really broken, or they would have these latent failures and then be brought into spec. And I was just wondering if you had any information on whether the fiber optic cables had any technology to improve that self-repairing.
to my knowledge, what they do is more or less mechanical. They encase them in concrete, and they typically bury them on the seafloor. It's not just laid across the seafloor, they're typically buried. They have a plow type of device, and that digs a trench, and they put the fiber optic cable encased in concrete down under the sea. So obviously there's places where you can, I'll call it an undersea manhole, where you can maintain it.
Okay, thank you, George.
That's the way it's like. That's the way it's like. Yeah, thank you. Okay. What I would like to do here is just to show you this preform and what we're with it. And I'd also like to show you light going through a fiber. And I have a flashlight and a totally bent piece of fiber if anyone is interested. Okay, thank you. I don't know if we're perfect. Can't see the stuff that
And while George is doing that, when George had mentioned that this would be his demonstration, one of the questions that I had asked him was based upon the fact that we know that in coaxial cables, we're dealing with a velocity, which is how fast is a signal traveling through that cable relevant to the speed of light at 300 million meters per second. And I was kind of surprised because I figured with fiber optics, it would be way up in the 90s, but it's not. Those signals are being slowed down. Of course, you know, at 250 million meters per second, you know, does it mean anything to us? No, but it may mean something in the long run, for example, transatlantic run. But I thought that was interesting. I was expecting the number to be so much higher.